Hi, everyone. Welcome to discussion one for 61C. This is going to be the last discussion. So I talked a little bit about it earlier, but it's going to be 2 hours long. We'll get a break in the middle, hopefully. And yeah, the general gist is it's going to be longer. It's going to be possibly a little bit more in depth. More time for a question Q&A. So it's also like the week after usually for the topics. So if you're feeling a little bit behind in lecture, you can take maybe the weekend to review or come to this section to kind of get a slower paced review. So let me share my screen. There we go. Can everyone see my screen? It should be blue. Yes, okay, cool. So yeah, welcome. I'm Caroline. I'm going to be teaching this discussion Mondays 1 through 3 every week, and my office hours. So I don't really have office hours. I'm going to be on call, which basically means I don't have scheduled office hours, but when the queue kind of gets nuts, I will be there. So yeah, but if you ever want to schedule a meeting to talk, or if you're feeling like you're behind or need advice or just anything like that, feel free just to email me. If you could title it like 61C or something like that, that would be really helpful just so I know what's up. Yeah, I'll talk about that in a second in the chat. But yeah, feel free to contact me whenever. If I don't respond basically within like 24 hours, feel free to ping me again. It's most likely like, oh, I marked it as read and then I went to go do something and then forgot because memory of a goldfish. But yeah. So some brief intro. So I'm Caroline. My pronouns are she, her, hers series. I'm a 4th year EXMCV major, and yes, I am dying right now, but it's okay. I'm from LA, if anyone else is from SoCal, and I was born in Austria, which is something that people don't really expect. Yeah, I'll send it actually in the chat. Give me a second. Here is my email. The slides also, for anyone watching later, are going to be provided. This time it's going to be provided after because I want to update it a bit more and add more explanations. But in the future, I'm going to try to get them out beforehand, probably in some post on Piazza. I'll figure out exactly where. It's most likely going to be a non-pinned post, but it's going to be linked under the central resources post, which will be pinned. So that way we don't have too many pinned posts at the top. But yeah, I think I've taught 61C for like 5th semester, 6th semester, something like that. Yeah, it's been a while. And if you ever want to talk about any random area of research, I am totally down because I've jumped through a lot. And now I guess I'm kind of like veering more into education stuff because education is on fire and on fire things are fun. And yeah, I like running, hiking, baking, arts and crafts, and I really like making Spotify playlists. So if you're interested in kind of building a playlist with me, feel free to scan the QR code right here. It's a collab 61C one. I might play it like in between stuff. But yeah, if you like songs as well, feel free to do it. I'll send the link later when I'm not screen sharing. But yeah, and I guess this is what I look like. You can see me on screen right now, but you'll probably be seeing half my face later on in the semester. But yeah, okay, really quickly, so some section logistics. So this is always going to be Monday 1 through 3. I believe in a week or two, there's going to be a holiday on Monday. So I'll figure out when my section is going to be afterwards. It might actually just end up being on the holiday, but you guys are totally not required to come out on a holiday. It's mostly because of room bookings. If room bookings don't work out, it'll probably be remote. In the future, when things do go back in person, it's going to be in SOTA 275, which is a lab room. It's unfortunate, but room bookings are kind of scarce and annoying. But the alternate Zoom link will always be this one, and it will be supported hybrid. So if you can't make it out, or it's too far, or you're not feeling well, or just for whatever reason, feel free to come on to Zoom, and I will try my best to make sure that everything is supported. But yeah, online will always be supported regardless of in-person status because there's a variety of reasons that people can't make it out, and it's not up to me to judge. And also remote's kind of nice because you can wear PJs. But yeah, lost section, what it means is maybe you're not feeling necessarily lost in a course, or if you're feeling lost in a course, but it's just a section that's kind of a little bit slowed down. We have more time for questions, to go into more explanations, more lecture time, maybe going through more of the questions, and just a generally more chill kind of a section. in the past, law sections for some of the like beefier topics later on in the semester, including C actually, tend to actually take up like the whole 2 hours with everything. So there's definitely not enough time to cover everything, but yeah, you're always welcome to come here if you're feeling like you may be a little behind or you just want more, I guess. Yeah, so it'll generally contain more mini lecture material. I'll usually have slides prepared for every section. And we should have time for most questions. And feel free to use the chat for questions. And this is something I want to try to support in the future, but I didn't get time to set it up today. But if you can't make it out to a section, but you have questions or something, I'm going to have an open form basically, and you can drop questions in there or just things that you want clarified during section. And because this will be recorded, it should be available afterwards if you can't make it. So yeah, are there any questions so far?
So when the sections are like hybrid, and then when we go back to like in person, but for those of us who will attend online, are we going to be still able to ask questions?
Yeah. So in person, it will really depend. When I taught CSM in person last semester, I was, I guess, sitting at my laptop and monitoring chat and also going to the board. And it seemed to be working out okay, given the feedback. I'm gonna see if I can snatch a few AI, so academic interns, they're being onboarded right now, to help monitor chat and to just make sure things are running smoothly, because hybrid is a pain sometimes. But if you have questions, it will be answered, is the short. Cool. Okay, so I'm going to briefly go through some of the slides. The slides are right now are definitely not comprehensive because lecture slides and then discussion slides, and then now we have discussion worksheet too. But feel free to stop me at any point. You can unmute yourself or you can drop it in the chat. If you're not comfortable with everyone seeing your question, you can always DM me and I'll try to get it answered. Sound good? Cool beans. Okay. So yeah, first up, well, I guess only topic really is number representation. So I think Nick mentioned, or Nick and Cece both mentioned this in lecture multiple times, and you'll hear this on end throughout the rest of the semester, but everything in computer is just bits. So there was a question in lecture of like, oh, how can this be represented? How can like memory addresses and structs and ints and things all be represented using the same format? And the short answer kind of is, the system itself decides how to interpret things. So it's not up to the program to say, hey, I want you to like look at these bits and like parse them in this way for me. And rather the typing that we do. So like in Java, if you remember, you have like explicit types. So you might have like an int or a char or a string or whatever. And that tells the Java kind of compiler translator to say, hey, I'm going to look at this series of bits as this particular type of data. And the same idea here applies to C. So in C, it's a little bit like one step lower than Java. So you'll see things like maybe like uint32t or like char star. We'll talk a little bit more about this later, but just kind of throwing some terms out there. So those types are basically telling us, us and the system, this series of bits is going to be this certain size, and I want you to interpret it this way. So it's not up to you to say these bits are special, but it's up to the system to understand that. So that's the general idea of how you can interpret those bits. So for example, if we have a binary kind of string here, 0110, 0001, underscore here is just to make sure it's easier to see how many bits you have and to be able to read it in a more a clearer way. If you interpret as an ASCII character, which is a 8-bit version, or yeah, 8-bit encoding of characters, it'll be interpreted as A. So something that you can do right now if you want is open up your terminal and type just Python to get the interactive interpreter. And if you run CHR, so character casting on this bit string, then it's going to return an A. And that's because we told it, hey, I want you to interpret this series of bits as a character and tell me what it is. And based on the standard ASCII encoding, because we didn't specify anything different, it's going to say it's A. So if you look in an ASCII table, it'll kind of match up. But if we look at it as a hexadecimal, which is base 16, then it's going to look slightly different. Yeah, this is the notation is slightly off. But if we look at it as a hexadecimal, I'll talk a little bit more about this later. It'll look actually different. So hex is basically saying, hey, I'm going to turn everything in base 2 into base 16, and we'll go over the conversion a little bit more later. But looking at this, we're going to interpret everything in groups of 4, because if we think about it, if we have 16 values that we want to represent, and because every single bit is either going to be 0 or 1, then we need 4 separate bits in order to represent all 16 values. And the reason for this is because, well, at every position we have 2 possible bits, and so say at position 1 we have 0, at position 2 we have 0, and then 0, 1, 1, 0, 1, 1. So to get the total number, we do 2 to the power of 2 because we have 2 positions. And so to get 16, it's 2 to the power of 4. So if we look at this, then we see, okay, 0, 0, 0, 1, this is going to be interpreted as 1. And if we look at 0, 1, 1, 0, then it's going to be interpreted slightly differently. So if we look from right to left as each individual value, we have, okay, at the 2 to the 0th position, we have a 0. At 2 to the first position, we have a 1. 2 to the second position, we have a 1. So that gives us 4 plus 1, which gives us 5. And so that gives a hex value of 0. Gives us a hex value of 0, 5, 1. So I'm going to be writing on the slides like this a lot for this particular one, just because it's really hard to draw with a mouse on here. But it'll be animated for when you want to go through the slides later. So up until this point, are there any questions? Okay, then moving on from this, if we want to interpret it as base 10, it's going to be slightly different again, because in hexadecimal, we only need 4 digits to represent each individual one. In base 10, it's going to be slightly different because we're just going to be adding up what we see here. So if we go from right to left, we have 2 to the 0, 2 to the 1, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, and then 2 to the sixth. So that gives us a value of 1 times 2 to the 6th, and then plus 1 times 2 to the 5. I'll go over this a little bit more in detail later on, but this is just generally to see how many different values we can represent with just the series of bits. So a question in the chat, so why was the hexadecimal just the first 4 bits? So not necessarily the first 4 bits, it's every digit is represented by 4 individual bits. The reason for that is because, say if we look at this and say, okay, so I have some number of slots here, and we don't know exactly like how many combinations we have. We're just going to give us like a couple of spaces. So at this first value, we can represent 2 different values, right? Because we can represent it as a 0 or a 1. Same with the second position, same with the third, and so on and so forth. So I don't know if you guys recall from like the mathy side of things, but like combinations and permutations. So if we have 2 possibilities here and 2 possibilities here, if we have both of these, positions, then we wind up having 2 times 2 possibilities because each position gives us 2. And so that gives us a total of 4. And so 16 versions is just 4 times 4, which means then we can use 4 different possibilities. Does that make sense? Yeah, sure. So can I explain what 2 to the 6 plus 2 to the 5 is again? Yeah. So it's base 10 unsigned. So I didn't write out the calculations. Oh wait, sorry, I realized I forgot the very last one. That might be why it was confusing. Sorry. So basically, this is the conversion of base 2 to base 10. So the way that base 2 to base 10 unsigned is converted is you just go from the least significant bit, which is usually the one on the right-hand side, all the way up to the most significant bit, which is on the left-hand side. And you take the value, so the bit value here, and multiply it by the digits value. So in base 10, like we have, so like if we have, for example, like 1, 2, 3, 4, 5, then we know that we want to calculate it as 5 times 10 to the 0th power, and then plus 4 times 10 to the 1st, plus 3 times 10 to the 2nd, and plus 2 times 10 to the, which direction am I going? Oh yeah, 10 to the 3rd, and then plus 1 times 10 to the 4th. So we know that this is the case because each of these are at a different position, right? So it's like ones, tens, hundreds, etc. The same general concept exists in binary. So it's just because we have two values instead, we're going to be using base 2 instead of 10 here. So if we consider that, then this is going to be, so it's going to be wind up being 2 to the 7th, and then 2 to the 6th, 2 to the 5th, 2 to the 4th, 2 to the 3rd, and then 2 to the 2nd, 2 to the 1st, and then 2 to the 0. So this is going from left to right. So each of these digits would correspond with this particular value. Does that make sense? Okay, cool. So I'm not going to calculate this out. This is just to show that there's a lot of different possibilities. So this particular string could also represent, for example, a memory address, albeit on a very small memory kind of space, but you could still use it to represent a memory address because we can just say, hey, I want to access this particular location in memory, give it to me, or this particular byte. Okay, so moving on to the next slide, let's skip past all of this stuff. So we have a lot of different representations that we can use. So from lecture, you might remember unsigned, which was mentioned on the previous slide, sign and magnitude for signed values. So if you want negative values, one's complement also for signed values, two's complement, which is the most common that you see used nowadays, as well as sign and magnitude. So binary to decimal base conversion. So you just add up the powers of 2 like we saw earlier. At the positions of 0, you don't add it. And then at the positions of 1, you do add it for the same reasons that you would do so in like base 10. Like if you have a 0, you wouldn't add that particular position. So if we had this example like earlier, then we would multiply it like this. So you could see each of these value digits corresponds to a power of 2 being multiplied. So calculating this isn't too important. I would say on exams, it's unlikely that you'll have to calculate by hand, like say, hey, this giant long string, like what does it equal? Because that just takes up time and it's not really useful in testing knowledge. It's more likely that you'll say, hey, I have a decimal value, I'm going to convert to binary, or have something shorter, for example. So this calc comes out to be 109. You can test it yourself later to see if it's actually true. If we have binary to hexadecimal, so like we said earlier, base 16, you read off groups of 4 bits at a time. So if you have 0, 1, 0, 1, 1, 0, 1, then the two groups that you have are 0, 1, 1, 0, 1, 1, 0, 1. So you can also see why, like earlier, we use the underscore, because without it, it's kind of confusing and it's really easy to mess up. Even after like teaching it for so many semesters, I regularly mess up in the conversions because I lost a bit somewhere. So it's very normal. And so the way that we can group these, so 0, 1, 1, 0 is going to be 4 because we have each of these kind of groups of 4 is going to then be interpreted basically in quote unquote, almost like decimal until you get past 10. So here we have 2 to the 0, 2 to the 1, which is 2, and then 2 to the 2nd, which is 4. So 4 plus 2 is 6. And in base 10, in hex, it's also 6 because 16 is past 10. And then the second digit is a 1101. So we can see here that it's going to be 1 plus 2 to the 2nd, which is 4, and then 2 to the 3rd, which is 8. So this comes out to be 16 in decimal. And obviously, like we can't have a digit that's, well, 2 digits long. So in base 16, because we've gone past the era of the numerals, we're then going to use letters. So a conversion between the two, I'm just going to write them here. Let me use a slightly different color. So we have 0 to 9 is just base 10 is going to be equal to 0 to 9 in base 16. But it changes after 10. So for example, 10 is going to be in base 10 is going to be equal to A in base 16. It's not 17. 11 in base 10 is going to be equal to B in base 16. Oh my gosh, I can't type. 12 is going to be equal to, I'm going to just give up on the subscripts. I'm going to add them in the slides distributed later, but you get the gist. So it's going to be C, 13 is equal to D, 14 is equal to E, and then 16 is equal, sorry, 15 is equal to F. So something that you'll notice with all of these is that Well, like with all other bases, you kind of run out of quote unquote digits when you get to 1 before the actual base itself. So when you get to 16, oops, when you get to 16, then it's just going to be a new digit. So it would be hex 10, for example. Oh my gosh, I cannot type. Hex 10. Does it make sense? Why? Okay, sorry about that. Let's see. Okay, so going through all of these, let's say I'm gonna split this in half just to make it a little bit more. Yeah, we're going speedy a little. So let me break this down a little bit more. So if we take a look at binary, for example, what would 10 be in binary? So if someone could drop in the chat. So 10 in binary, remember? Or like, okay, 10 in base 10 represented in binary form, I guess. Yeah, exactly. So you have 1010 is equal to base 10, which is equal to 8. So I'm just going to actually bump them all to new lines like this. Maybe I'll make it a little easier to see. So we see something special. So let's actually start from base 9 above here. So when we have base 9, we know binary, it's going to be, okay, it's going to be 0, 1, 1, or sorry, 1, 0, 0, 1. So we know that it's going to be 1, 0, 0, 1 because this is 2 to the third, which is going to be 8, and then plus 1. So that's going to actually equal 9. So once we add 1 to that, we can see that it's bumped to binary. This is the binary value. Does that make sense so far? Okay, so once we have the binary value, we can interpret this as like, oh, let's just convert it to base 10. It's going to be base 10 because we've just added 1 to 9. So that makes sense. But because base 16, so like digits as a rule of thumb can't be like 2 digits, because when you're representing, say, a hex like string, you don't want to be writing like, oh, like 10, 15, 13, something like that. Like it would look kind of weird, right? If you had to write it like that. So that's why they go into letter form, and they just start with A just because A is like the first letter of the alphabet. So there's no really rhyme or reason to that. So we just say, okay, we're going to start with A as base 16. Now let's add 1 to 10. So in binary, that's going to be 1, 0, 1, 1. So this is going to be equal to 11 in base 10. And then we're just going to go 1 up in terms of the alphabet. So now it's B. Same with C. So if we go here, then it's going to be 1, 1, 0, 0 is equal to the 12. And that's going to be equal to C base 16. Let's add the post subscripts to make it a little easier. And then same, we're going to just keep doing this. So we keep adding 1. So 1, 1, 0, 1 for 13, which is equal to D. 1, 1, 1, 0 for 14. And then 1, 1, 1, 1 for 15. So it's at this point where you can see kind of like, okay, so we know hex values are supposed to have 4 binary digits. So we've just used up all our binary digits. And if we add all of these together, it's going to be 8 plus 4, which is 12, plus 2, which is 14, plus 1, which is 15. So cool, that gives us a 15, and then which is going to be equal to F. And so if we add 1 to this to get 16, let's bump this to the next row, then what it's going to look like is actually going to be 1 and then 0, 0, 0, 0, because we've now kind of have to carry it over, just like in regular decimal addition, right? So if we take a look at this hex digit, it's now going to be 0, which is corresponding to this. And then this next kind of hex digit that we're looking at has 4 kind of floating zeros that we're just going to add to it because hex digits are 4 bits. And so this then gives us our hex digit of 1 here. Are there any questions for how we got here? So wait, is not, wait, sorry. 11 base 16 equal to B10. So the way that, yeah, so the way that it works is the base, like if you have something in like a base and you're representing 1 digit, you only want 1 digit to be there. If we have, for example, 11 base 16, what that's actually going to be representing is it's going to say, okay, I'm going to have 1 times 16, 16 to the first power plus 1 times 16 to the 0th power, which is going to give us not what we want, right? It's going to give us 16 and instead of 11. Does that answer your question? Yeah, of course. I'm gonna give y'all a second to digest that. Yeah, so let me re-explain why 16 is equal to hex 10. So it can be a little bit confusing because each of these digits is like, it looks like a normal, it looks like a normal decimal value. So like, it might be a little clearer, for example, we look at something like that. Or let's not make it so much. Let's make it like a little bit less. Let's do 3. There we go. So I'm just going to use this as an example. For 2 hex digits. So how we would calculate this would be, okay, well, if we look from left to right, this is at 16 to this first power. So we have 3 times 16 to the first power. I don't know why I made that value, but and then we have plus 15 times 16 to the 0th value, right? So this is corresponding to our F value, which is 15 in decimal terms. Almost always you'll want to calculate these values in terms of decimal, just because it's kind of what our brains are used to. But in kind of like computer world, the bits are easier, but writing a single like string of 32 or 64 bits is kind of annoying. So that's why hex is a thing. So to kind of get to your question of why I think I lost the chat at some point, but yeah, to answer your question of why it is, it's because it carries over, because we have all the ones in this single 1 hex digit already filled up. So in order to get to the next value, to +1, we have to carry over the 1, and then we implicitly fill in the rest of the digits as like zeros because they're not currently being occupied. And so that's how we wind up getting this final value. Does that make sense? And yes, so would 17 in hex be 0x11? Yes, it absolutely would be. So I encourage, on the worksheet itself, there's a lot of practice in converting back and forth. We'll do some examples later after like the mini lecture part, but I definitely encourage you to just kind of go through and convert some just to get more familiar with it. What I would actually recommend is like looking at this chart, like 0 through 9 is pretty easy because it matches what we normally see. But I would definitely recommend kind of memorizing, getting really used to looking at these patterns and just being able to eyeball say, oh, like I see 1100, it's a C. So this takes a little bit of time, but it makes conversion a lot easier later down the line. Cool. Okay, so let's move on to the next part. Okay. So question, how do you represent a power of 2 in binary? So these are just some quick tips and tricks to make computation faster, to just reduce time overall. So for powers of 2, only one of the however many bits that you have is going to be 1, and the rest are going to be all 0. Does anyone know why that might be?
Because it's like a power of 2, right? So it doesn't have like a remainder or anything. So if it's a power of 2, like it's 16, then it's definitely like 2 to the power of 4, where all the rest are like 0.
Yeah, exactly. Because when we're working in binary, like all the digits are already powers of 2. So we don't need to add anything on top of that. So your explanation is exactly correct. So if we have, for example, 2 to the 5th, we only need this digit to be 1 to be 2 to the 5th, because we have what, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5. So we only need that one digit there. So question, how would you represent 1 less than a power of 0 really quickly? So without thinking, what would that look like?
Can I go first?
Yeah.
So you basically represent the power of 2 itself, but then the rightmost digit, you just, instead of a 0, you just add 1.
So I think what you're thinking of is 1 more than a power of 2, because you add 1 on top of that. So what Zach said in the chat is exactly correct. It's just going to be all 1. And if you think about it, the reason is like, if we think about it in base 10, if we have say like 100, and then we want, or like say a power of 10, so 10 to the say 2, 100. If we want 1 less than that, we're just going to take that 1 and then use it as like a carryover. I've forgotten the terms at this point. It's been too long since elementary school. But you kind of like use that, and then so you wind up with all 9s, right? So the same kind of concepts holds here, where you taking that 1 that we see here, And then we're saying we're going to use that and kind of carry it backwards all the way through. And so if you subtract 1 from that, it's going to wind up being all ones, just one kind of number fewer. So if we take a look at this, for example, if we have 31, it's going to be 2 to the 5th minus 1. And that's a 2 to the 5th we already know before is 1 with 5 zeros after it. If we subtract 1 from here, then we're going to get a 0 in the first one because we've used that 1. And then we've used that 1 to kind of carry over all the way to the end. And so we're going to wind up with all ones here. So if we go the opposite direction and we say, okay, if we have 31 plus 1, does that get us to 32? And so if we add 1 here, we say, okay, 1 plus 1 is going to be 1, 0. So we have a 0 here. We're going to carry over the 1. 1 plus 1 is going to be 0, carry over the 1, so on and so forth until we have no more ones, and that final 1 is going to drop down. So it does give us our final value. So do we have to get rid of the 1 at the end place? Yes, exactly. So it's going to be 1 fewer in terms of number of digits that you actually see that's not filler zeros. But yeah. And then can we say we're flipping it? I guess in theory, yes. In theory, yes, you can say that. That's just because it's like it's binary and there are only 2 values. So if we're hex and then we have to do that, it's not going to work because flipping hex like just directly like that as hex values won't necessarily work. But yeah, you can just think of it as like all 1 fewer bit with the largest digit possible. So if we have, for example, a power of 16 minus 1, then what are all the digits going to be filled with?
0, 1, 1, 1.
Huh?
0, 1, 1, 1.
Yeah, 0, 1. But if we're writing in terms of hex, what will all the digits look like? Not binary. So what's our largest hex digit that we can use?
15, right? Which is F.
Yeah, so 15 F, exactly. F's in the chat. But yeah, if we have, say, power of 16 minus 1, it's going to be all F's. And you might like see this commonly as, for example, like you're like, oh, I'm going to have like the largest possible digits. Then it's just going to be like 0 hex F, 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 F. Yeah, so there we go. So like that's something that you might see often as like filler values. We'll actually talk about this later. This is a kind of special number. You'll see this a lot in C, used as constants and stuff. But yeah, exactly. Are there any questions? So, okay, question in the DMs. What does the F, or what do the Fs mean again? Yeah. So if we say like we have 16 to the power of n minus 1, what the outcome is going to be is basically it's going to have n minus 1 digits of F in base 16. So that's basically what it's showing. Because the F is the largest digit, I guess, in base 16. So when you subtract 1, it's going to wind up. It's kind of like, for example, 100 minus 1, 1,000 minus 1, 1 million minus 1. It's going to be all populated with 9s, right? Does that make sense? So you can think of like the F's basically as the quote unquote 9 of base 16. Cool. Okay, moving on, representing negative numbers. So before we get into this, into this entirely, we're going to talk a little bit about signed numbers. So there was a question at the beginning before section started of, for unsigned values, why is the range 0 to 2 to the n minus 1? So let me actually write this out. I will just duplicate this slide to use a scratch paper. Yay, normally I'd be writing on a board for this, but I guess we're using slides for now. So for unsigned values, I don't like this one. This should be normal. There we go. Y is the range. Y is the range for n bits 0 and 2 to the n. So this is a really, really valid question. It can get a little confusing sometimes, especially because like when we talk about signed values, the kind of ranges shift a little, and sometimes it's 2 to the n minus 1 and then minus 1 and so on and so forth. So the reason is because, well, at the end of the day, we want to represent 0. So we can have unsigned and say, hey, we can do like, for example, if we have like, we could technically in theory have 1 through 2 to the n. And that would look really, really nice. Like, it's not 2, sorry, 2 to the n. And oh my gosh. And we can have 2 to the n, and that would look really, really nice and whole. But we have the big issue of not being able to represent 0. And 0 is a really fundamental concept in CS because, or just in computers in general, because it's usually used as a not, false, null, empty set, etc. So it's really, really useful beyond just kind of like calculating things. So in order to represent 0, we're going to take away from our largest range because it's much more likely we're going to use 0 instead of, say, whatever 2 to the n is. So if we have 32 bits, when are we going to use 2 to the 32, right? It's just as good as 2 to the 32 minus 1. So we represent 0 by taking away the 2 to the n value. That's less useful. So by doing that, then we shift our range entirely down. So we have then 2 to the n, or 1 and then 2 to the n, the whole thing minus 1, which gets us to our final range here. Are there any questions? Yeah, so can I give an example for n equals 3? Absolutely. So say if we have n equals 3, we know that we can represent, say in theory, if we just had 2 to the 3 or 2 to the third power, that's going to give us 8, right? So let's see what we can represent here. So we have 0, 0, 0, which is equal to 0, 0, 0, 1, which is equal to 1, 0, 0, 2, or what am I doing? 0, 0, 2, 0, 1, 0, which is equal to 2, 0, 1, 1, 3, and then 0 or 1, 0, 0, which is equal to 4. Something you might notice right here is what we talked about earlier. Powers of 2 are always just going to have 1, 1 in the representation. 1, 0, 1, which is equal to 5, and then 1, 1, 0 equal to 6, and then 1, 1, 1 is equal to 7. So we notice even though 2 to the 3 is equal to 8, we won't actually be able to represent 8 in our unsigned schema because we only have 3 bits. And by our also understanding of the representation earlier, we know that 8 is a power of 2. So in theory, it should only have 1, 1. So this wouldn't be a valid representation anyways. So we would have to have 1 extra bit in order to be able to represent 8. Does that make sense? Yeah, of course. Are there any questions for unsigned? Okay, something to note really quickly before we move on is excluding biased notation because it's kind of its own weird shifty thing. Unsigned is going to have, with n number of bits of all the representations, it's going to have the largest upper bound. And if it doesn't make sense right now, why? We'll revisit this in like 3 minutes. So just keep that in mind. This is going to have unsigned. So we're going to come back to this a little bit later. Feel free to mull on this as to why that might be. Yeah, we're going to talk about sign notation now. So sign notation, you might have heard in lecture, there's a bazillion different ways. Why is using the unsigned representation not enough for our usage? So if you've taken a look at the homework or watched lecture, or if you think about it a little, we use unsigned numbers a lot in daily life, but we also use signed numbers a lot. Like, what are some ways that we use assigned numbers? Sorry. So just something that you use in your daily life.
Wait, signed or unsigned?
Oh, sorry, I'm sorry, signed. Temperature, yeah, temperature. I guess in Berkeley, we don't really have negative temperature much, but I guess if you live in Chicago or like anywhere else, basically you will. Other thing, GPA, oh my gosh, no. I was gonna say debt, so I guess kind of the same, yeah, bank account, yay. So there's a lot of uses for going into the negative businesses. I don't know. Yeah, I don't know, we're all thinking really negative, but I guess temperature is the one positive thing. But yeah, there's a lot of uses for assigned numbers. So it's really useful for our systems to be able to represent that. So we can't just have that. What if we have fractional numbers? That's another reason, right? Like signed numbers are very useful, but we also use fractional numbers a lot, like change that you might get at the grocery store, or splitting a meal between friends, or just whatever else that you might have. Tuition is usually has some weird number of cents after it, stuff like that. So we'll talk about fractional numbers and decimals and things like that, I believe next Tuesday, and in 2 discussions time. So yeah, this is under floating point. We won't talk about today. Don't worry if you aren't sure. I've just realized every negative number evokes a negative emotion. What representations can we use then? Sign and magnitude. We talked about this a little in lecture. Basically, the general idea is, okay, we have n number of bits. We're going to use the leftmost bit, so the most significant bit, as our signed representation. So it's almost like it's going to be a plus or minus, but we're just going to use it as bit form instead, because we can't represent plus or minus in a bit easily. And then the rest of the n-1 bits from the rightmost bits, those are the ones actually going to represent the value. So we're going to take the unsigned value of the n-1 bits and then calculate that and then attach whatever the 0 or 1 is at the beginning. So pros, well, pros is it's really easy. We don't have to do many calculations. We can just look at it. So sign and magnitude, typically, if it's a 0 at the very beginning, it's a positive, and if it's a 1 at the beginning, it's a negative. Nice and simple. And then we just take the rest of the bits and say, what does this look like? Calculate that and then call it a day. What are some cons? Well, okay, say if we have all zeros in the n-1 bits, and then we have, say, I'm going to type this in the chat. Actually, no, I'll type it on here. No, I just closed the chat, sorry. Let's say if we have versus, what do these 2 numbers represent? And yes, I see your question in the chat. I will get to it in a moment. So feel free to toss here. So we have an answer of 8 and 0. Remember, we're interpreting it as sign and magnitude, not as unsigned. So the first bit is positive. Okay, so we have a negative 0, and then we have, yeah, so we have a negative 0 and then a positive 0, or a standard 0. So yeah, the top one, if we interpret this, we're going to say, okay, well, most significant bit, that is equal to 1, which means that we're going to have a negative value. And then our rightmost n-1 bits, well, that's going to equal 0, 0 binary, 0, 0, 0, which that is going to be equal to 0. So our final answer is going to be negative 0. Not much of an issue. 0 is positive, negative. We don't really care. But if we look at this, we have our most significant bit is equal to 0, and that's going to tell us it's a positive. Our n-1 bits are 0, 0, 0 again, and that's going to be equal to 0. And so our final value, like in the chat we're saying, is going to be a positive 0. So as humans looking at this is not much of an issue, because we can just say, hey, they're the same thing. We don't really have to worry about it. But we'll learn later in the course that everything in the system has to be programmed through hardware. And having 2 separate zeros can get really annoying really quickly when doing different types of calculations, because we have to compare against one and then the other, and we have to say, hey, if this is a positive 0 doing this calculation, we have to go through this kind of path. If we have a negative 0, we have to go through this separate path. And logically, it just doesn't make sense to have 2 separate zeros. So we say, okay, this is not great for that reason. So then we have our ones complement. So I'm going to temporarily just delete this. I'm going to separate it into different slides later on, so it's a little bit more clear. So I'm just going to delete this for now. Actually, I'll make a copy and then I'll delete it, just so that we have everything together. So, oh my gosh, there we go. So then we have our ones complement. So does anyone remember from lecture what ones complement looks like? Or generally,
it's pretty kind of like signed. It's kind of like signed. You have the most significant bit for the sign, and but then for the negative, you just flip the bits.
yeah, exactly. In the chat, and like you said, yeah, So to get the negative version of any value, we're just going to flip all the bits. So in theory, that sounds also pretty easy. So if we go through and do an example, let's say we have a very simple value. Let's not make it long. Let's say we have 4 that we want to represent. So this is equal to positive 4 in our opinion. And then let's say, okay, we have 4 bits that we're going to do. So it's going to be equal to positive 4. And then if we flip all the bits, so we negate everything. So you'll learn later that this is called a bitwise operator. It's going to basically act on every individual bit. And this is a not. Don't worry too much about it now. We'll cover it in depth later in this semester. So if we just flip all the bits, it's going to be 0, 1, 1. So this is going to be equal to negative 4. So something about this that's really interesting is, well, okay, let's do another example. Let's do 5. And that's going to be binary 0, 1, 0, 1. This is going to be equal to positive 5. And then our negation is going to be, oh wait, I just realized this notation is wrong, so we're flipping this, but I'll just write it like this. So if we flip everything, it's going to be 1, 0, 1, 0, and this is going to be equal to negative 5. So something that we notice is it's a little bit strange because, well, we can see that on the positive side, we have, okay, this is increasing technically. Like if we just look at everything in an unsigned form, this is going up the number line, right? Because we're increasing in digits. And this is increasing in value. But the other way, if we're looking at it, well, this is also strange because this is technically increasing in magnitude, but it's going the opposite direction. So it's kind of like the number lines are diverging in that sense. And so it makes for computation to be a little bit funky. And so we just don't really like it that much. And this also still presents the problem of double zeros because remember, as we have 0, 0, 0, 0 is equal to 0 in binary, but that means we still have a negative 0. So that doesn't solve that problem. It's just going to be 1, 1, 1, 1 is equal to negative 0. And that's kind of awkward, right? So pros, it's again easy. Cons, it doesn't really solve our main problems that we have. So if we move on, oops, didn't do that. If we move on to the next kind of representation, 2's complement, spoiler alert, we talked about this earlier, and it's the most common one that's being used. So yeah, so to answer, we'll never actually really use 1's complement. Almost definitely not. It's just really good to understand. And again, like it's not really like too challenging just to flip all the bits. So I don't believe we ever really asked you to do that kind of thing, but this is just kind of the order in which the thought process progresses. So like, why is 2's complement like so complicated? Why do we have to do this flipping and then adding one thing? That's kind of why it's to get rid of this problem. And so, okay, moving on to 2's complement. This is probably the most kind of complex for one of these that you'll be calculating. And so the pros to this, oops, I guess I didn't write a pros and cons, but to kind of the pros of this is, well, things kind of operate in one direction. As in, if you go up the number line, we're going to strictly increase in terms of our binary values, which means you'll keep adding 1, and then in the actual values, values themselves, it'll also keep increasing in 1. So binary form of 0 will not like look greater than, say, binary version of 10. Another really good thing for this is the fact that we won't actually have a duplicate 0. And the reason for that being is because to convert to get the negative, what you have to do is take positive, bitwise negate the positive version, and then add 1. So what we do here is we effectively shift some of the number line up by 1. And so that kind of, originally we had an overlap at the 0, and now that we shift some of it up a little, then we'll no longer have the issue of kind of repeating the 0. So okay, to convert to a binary to 2's complement, you just flip everything and add 1. Yes, exactly. Does that make sense? I don't know, like it's a little bit confusing. Yeah, okay. Which part are you confused about? And like it's all kind of like confusing, but just so I can get a better direction. we're doing an example help. Okay, let's see you represent a binary in 2's complement as well as normal binary. If they're positive, they're the same. Yes. So yeah, unsigned, I think what you meant by binary is unsigned probably. So unsigned and positive 2's complement will look the same. It's the negative that will look different. So the negative takes the unsigned version, negates all the bits, and then adds 1. So let's do an example for this. So let's say we want to represent, say something interesting, negative 13. Okay, so, well, we want to the first thing is we want to get the positive version. So positive 13 is equal to, does someone want to pop it in the chat? Oh, what was the question? It was, what is positive 13 in binary? So yes, 1101. I'm getting a call. I will answer that later. So 1101. So if you're a little confused as to how that happens, so we have 8 plus 4, 12 plus 1, which is 13. So we're actually just going to give that leading zeros just to make it very clear that it's positive. So what this is basically called is like in any question, you'll basically see, so given a digit with 8 bits or given 8 bits, how would you represent this? So you'll almost negative, or sorry, not negative, you'll almost never just see something cut off like right here if you're trying to say represent a positive value, because usually the 1 here would represent that it's a negative. So let's say 13 looks like this. Okay, cool. The next step would be to negate everything. And so that gives us 1, 2, 3, 4. There we go. So that gives us 0 binary 1, 2, 3, 4, then 0, 0, 1, 0. Cool. That doesn't get us to where we need to be yet. So now we're going to do the final step, which is to do +1. And so if we do +1, okay, that's going to look like 0 binary 1, 2, 3, 4, 1, 0, 0, 1, 1. So I realize the contrast is not great here. Let me make this white. I think it'll be a little easier to see. So this gives us our binary representation of -13. So something that you can use to double check is, well, okay, do we have leading ones? In this case, yes, we do have leading ones indicating that it's negative. So in 2's complement, it's still kind of, if you have leading ones, it's a negative. If you have leading zeros, it's a positive. And these zeros, basically are saying, I'm going to make your calculations a little easier for you. Because if we didn't have that, for example, oops, strike out, there we go. If we didn't have that and say we did our conversion like this, then it would look something along the lines of this. So the non-crossed out parts, and that can be confusing to the naked eye. So we always have these buffer zeros. So that's why we have the leading digits. It's just to kind of make it clear to ourselves. And also in questions, it'll almost always be the case you have more space than is needed to actually represent your value. So in this case, we actually only needed 4 digits to represent positive 13. But a question will almost never say, given 4 bits, how do you represent negative 13? Because this is just like wrong. That makes sense? Cool. Okay, so the question that I'll come back to, so how will C know how we're representing numbers? So the question kind of was, how do we know the difference between signed and unsigned values? And the reason for that is like we said at the beginning, everything is bits. The computer won't know unless we tell it that, and we tell it that by kind of programming the system to recognize that when we're compiling, for example. And the second thing that we do is to make sure that things are typed properly. So for example, if we have, I believe you guys have seen a little bit of C code at this point, so I'm gonna just like write one thing, but this is just like literally for an example. So say if we have U int WGT, unsigned, or unsigned is a keyword, so that was bad to use, but say unsigned value is going to be equal to, let's say 8. And then we, in the next line, semicolon, because and then say in the next line, we say, okay, we're gonna do unsigned val is equal to int 32t of unsigned val. So this is like 61A level of weirdness. But basically what happened here is, okay, we have a 32-bit value that is going to be 8. So what it looks like is like a bunch of zeros here and then 1, 0, 0, 0. So this is representing our 8 form. And then in the next step, we say, okay, we're going to just cast this to being a signed value. So it's going to actually be, or I realize this is a really bad example. Let's do 8 bits instead. Let's see. And then we'll do 1. So basically what this is representing, what this is representing is going to be 8 bits worth of 1, 2, 3, 4. So we have 8 bits worth of material. And so when we convert, so if we represent this as a signed or unsigned value, it's going to be equal to whatever 2 to the 7 is. I think it's like 128, something like that. But if we cast it to a signed value, so int 8t here, it's going to interpret it differently. And so this is going to look at this and say, hey, this is a 1. It's going to be negative. We only have 8 bits, so I'm just going to take it as it is and then interpret it using 2's complement to be whatever negative value this is. So is saying is this explicitly saying this is, wait, sorry. Can Michael, do you mind clarifying your question? Okay, in the meantime, I'm going to answer Renee's one. Is this how you declare stuff in C, the shorthand? You went 8t stuff. There's going to be shortcuts. This was just to kind of explicitly show. This is like the non-typecasted form. So you talk about typecast in C as well, which is basically an easier nickname for certain like longer types. And so this was just showing that we have 8 bits to work with explicitly. I don't think you should have to use this form until maybe like project 4. So you'll definitely get more familiar with it as time goes on. Is there a shorthand where symbol for showing that it's 2's complement? Not exactly. If you're talking about exams or homeworks, it'll say that like interpret this using 2's complement. If it's on like in C code or whatever, it's just implicitly what's done. It depends on the compiler, I will say. Or it also depends on like what system you're running it on. You can just basically assume it'll be 2's complement unless you're doing something wonky that specifically wants it to be something else.
Is there supposed to be a dot notation?
Is there supposed to be a dot notation?
Yeah, like yes, between the int 8 underscores t dot unsigned.
Oh, like this?
Yeah.
Oh, okay. So dot notation, this is venturing into C territory. I won't talk too long about this, but I can say a little bit after. So dot notation is for accessing fields inside structs or unions. And we'll talk a lot about this next week on Monday. So this, because it's not a structure, it's an implicit data type. We don't need to do this. This parentheses thing is a casting. So in Java, you might have seen the CS61C where it's kind of like, oh, I'm gonna like, you can cast up, right? Like, so for example, if you have a animal like super class and then you have a dog underneath that, you can cast like the dog object to be an animal. So this is kind of like the same way. It's kind of like casting up. You can say, hey, this unsigned value, I actually want you to interpret it as a signed 8-bit value instead. Does that make sense? Why there's no dot notation?
Yes.
Okay.
So again, like we can do app. So that's app casting, right?
That's what?
App casting, like going.
Well, not exactly. It's just
Wizard
casting. Typecasting is something else. In the interest of time, I can answer questions about it after, but not right now.
Okay, thank
Just
you.
remind me. If you're given some binary string and you must interpret it using 2's complement, you subtract 1 and flip all the digits to get the magnitude. So what you can do, yeah. So if you're given some binary string and you must interpret it. Yes, sorry, it took me a second to process, but yes, you can do that. You can subtract. There's also a neat trick that I can show again after a discussion, just because I think like, yeah, we are over halfway through. But I will say like, the way that you can interpret it is basically say, oh, if I have, it will be obvious in the sense that like, for example, like if we have this binary string, 0b1111, I'm gonna undo this. And so if we have this, let me make this dark again. No, other way. Okay. So if we had this original 11110011, and it's asking you what is this in decimal or base 10. So what you can do is like what you said. Okay, I'm gonna subtract because you know that it's like, I guess, okay, I'll explain this. If you only have 8 bits worth of kind of space and you have a 1 at the very beginning, it's always going to be a negative. Because the way that kind of it works out is 2's complement is always going to have the 0 first, most significant bit as a 0, and then as for positive, and then as a 1 for negative. So if you have the 1 at the beginning, then you can say, okay, I'm just going to interpret this as a negative number and then kind of do the reverse to get the official positive number. So you don't have to worry about the leading ones. You just have to see if the first value or first bit of that entire bit string is 1 or 0. Does that make sense? Okay. So in the interest of time, I'm going to move on. Let's see. Okay, I'm going to skip that all the way to here. So because bias notation does show up occasionally. Bias notation, again, it's not the most common version just because of the nicheness of which it exists. So I'm going to just kind of skip over these main things, and then we'll kind of go over them in the discussion worksheet itself. But the ideas of bias notation is just to say, okay, well, all of these other kind of sign notations, we mostly have equal kind of ranges on the left and right because we want to divide it evenly up between the positive and the negative. But sometimes we have extremes, say in the negatives, or extremes in the positives. Say, let's say temperature of the sun, going to be really, really positive, no negatives there. Or say temperature of the Antarctica in the winter, that's also going to be all negatives. We don't need positives there. So it gives us more flexibility in terms of where our range kind of slides on our number scale. So the way that that kind of works is we start out with our unsigned notation. So remember, if we go back to unsigned notation here, our range is 0 through 2 to the n minus 1. So we take our range here and then we say, okay, we're going to take this and then we're going to add some bias. So I know there's been some confusion on Piazza about this, about like whether you subtract bias or add bias. I'm going to go out and say, like, I think we've been trying to standardize it as plus bias. You'll see it on the internet as sometimes like subtract bias, etc. In this class, we're trying to standardize it as plus, and I think almost every TA you talk to is going to try to push for that. So you can just kind of internalize it as we're going to add a bias. So the bias itself can be positive or negative, depending on which direction you want to shift it into. If you want to shift it into a very standard, like positive negative split, the standard bias is going to be equal to 2 to the n. 2 to the n minus 1. No, sorry, minus 1 minus 1. There we go. So this, oh my God, that's not right. Sorry. There we go. 2 to the n minus 1 minus 1. So this is the standard bias because what we're saying is, okay, we're going to give ourselves either one extra positive or one extra negative because we still have to represent the 0 and we have an even number of values that we can represent. So we either sacrifice something from the bottom or we sacrifice something from the top. And so if we have a standard bias of this, then we can say, okay, if we, oh, sorry, this is going to be negative, I realize, because this is our standard bias. There we go. So what we're going to say here is we're going to have one more negative number than positive number. So this is going to give our final bias to be negative 2 to the n minus 1 because we're dividing the entire split of like values that we can represent in half. And then we're going to do one lower than that. I will show an example of this in a moment. And so that means our upper bound is going to be 2 to the, no, sorry, nope. there we go. It's going to be 2 to the n minus 1. And we can see this in action by saying, let's say we have n is equal to 3. So that means our standard bias is going to be negative 2 to the third minus 1 minus 1, which is equal to, so 2 to the second, which is 4, minus 1 is 3. Yeah, negative 3. And so that's going to give us a range of negative 3 through 4. And we can see that that represents 8 values total, but it's shifted everything down. Are there any questions? Okay, is this sense, it makes sense, or everyone is confused? Suspiciously silent. Yes, that is how I feel. Oh, okay. Oh, suspiciously silent is not. Okay. So if you still have a question about it, yeah, take some time to let it sink in. The slides will be available after. I'm gonna, if you can see the speaker notes here, that's where I typically add like my own notes that don't fit on the slide that like I verbally talk about. So hopefully that'll help. It does take time, it takes practice. So if it's not immediately clicking, that's totally okay.
Excuse me, for the line 1, can you go over line 1 again?
For what?
Can you go over line 1 again?
Here?
Yes.
Okay. Yeah, so the general idea is, so we have here, we copied this from our unsigned state. So the idea of bias is we have our unsigned range, and we're going to add some bias to that to either shift it in the positive direction if the bias is positive, or shift it in the negative direction if the bias is negative. So don't think about like ever subtracting anything. It's always adding a positive or adding a negative. And so the bias here, it can be positive or negative. And the standard bias, aka like if we say, oh, like we don't specify how to calculate the bias, like sometimes you'll see, oh, the bias or offset is going to be like positive 31 or negative 125. That already gives you what the bias is. But if it says, oh, we're going to have a standard bias, it's typically going to fall in the range of this. So I believe if you look at the worksheet, I realize I haven't been screen sharing the worksheet, which is fine because it's kind of up here. But let's see if I can find it. I'm not actually sure it shows up on here. Yeah, okay, it doesn't actually show up on here, it appears. I'll add this to the notes, but basically the standard bias idea is, oh, this is what we're going to default to in order to create a pretty like evenly split range. So we can see here on the example, we have 3 negative values, 1 0, and then 4 positive values. Pretty standard. And so that's how we calculate the bias itself. So we do the n minus 1 part to the power of 2, or 2 to the n minus 1 because, so if we have, say, we want to split something in half, and originally we started out with 2 to the n number of objects, and we want to divide this by 2. In other words, this is equal to 2 to the n minus 1, right? Because we're taking 1 away from what we're multiplying. And we then shift that down by 1 and then try to make that our kind of lower bounds. So there's like, it's kind of depends on what you value. Like if you value more negative numbers, the standard bias is going to have like going to shift down. If you have more want more positive, your bias is going to shift up. But usually it will fall somewhere here if it's not specified. Does that make sense?
Sorry, so -1 because we want like to have more negative numbers.
And you mean right here?
Yeah, and
So
also
we're gonna have fewer negative numbers actually, because this like the negative here is kind of like negating everything. Let me just double check to make sure that this coincides with lecture because sometimes it does change. Give me one moment. So you have kind of like 2 options. You can either have like the parentheses or not the parentheses. So actually something that's good to keep in mind for later in so in 2 weeks time, we're going to be talking about floating point, and that's also going to have a bias. And it uses the same kind of setup as this. but I believe the way that the bias is calculated is different. So it can be confusing. So you want to be able to keep the two kind of straight in your head. So let me just double check to make sure I'm not sharing the wrong information. Let's see. Yeah, okay, so it does have the parentheses here. So this is basically having one fewer negative number because we calculate some positive offset and then we negate that. So if we're subtracting from this positive value, it's going to give us a larger negative value, if that makes sense, or a more positive negative value.
And we divide by 2 because like we want, I mean, we want to have like positive and negative, right? That's why we divide
Yeah.
by 2.
Because you want to kind of generally split in half.
Okay.
So we're learning the ranges and stuff. So eventually we'll have to determine what number system is the best in upcoming projects. I don't think you do have to. Let me think. I think the one time that you would have to kind of represent something would be in project 3, which is a CPU project, because you're actually like encoding the way in which things are interpreted. In terms of number representation, you'll almost, I want to say this with a grain of, don't quote me on this, but you won't ever have to physically represent bias notation, I believe. It's going to be choose complement for anything like any arithmetic. Why are we learning this then? Because it is useful. It's basically because we don't want you to implement something like even extra. Project 3 is already really long as it is and pretty difficult in other regards. It's kind of like understanding this is kind of building up the foundation for later things, because if you're say interested in the hardware side of things, there are ways in which this is used in 152, which is more computer architecture, and then 151, which is digital systems. If you're like working in like more like theoretical stuff, I guess it's less necessary, but at the end of the day, like weird things come up where you're like, oh yeah, I learned bias. This is useful. I would say bias notation is also useful in understanding floating point, which is the basis of all decimal systems in computers.
So I have one more question on this. So we know that like the range is from 0 to 2 n minus 1, but when it comes to dividing it by 2, we just divide 2 to the n by 2. Why are we not like dividing 2 to the n minus 1, the whole thing by 2?
Like this entire thing?
Yes. No,
Um,
like 2 to the n, and then not to the exponent, but on the side minus 1 divided by 2.
oh, you mean this?
Yes, yes.
Oh, gotcha. Okay. The reason is because here, this is the upper bounds in terms of like what we can represent. The number of values that we can still represent is still 2 to the n, because we have the 0, right? Because this is counting a 1. If we start counting from 1, it's going to be 2 to the n minus 1. But if we start counting from 0, it's still 2 to the n. So we're taking the total number of values that we can represent, having that, and then the minus 1 here corresponds to this minus 1 over here, because it's saying we need to take something from somewhere, either the positive or negative side, to represent a 0. And in this case, we compromise the negative side by taking one extra value from there to represent 0. Does that make sense?
Yes.
Okay. Okay, so let's see. We have technically 35 minutes. How do you guys all feel about a break versus just continuing? Continue? Keep going? Dang, you guys are hardcore. Okay. Let me switch over. I'm gonna have a cleaned up version of the slide. Oh, okay. Some person want to break. Okay, some DMs break. Okay, yeah, there's no harm in asking for a break. I will stay over a little bit just because it can be pretty confusing, and time-wise, I will give, let's say, okay, 3 minutes break until 2:28 to use the restroom, get some water, get a snack, get lunch if you haven't eaten lunch yet. I need to use the restroom. So I'm gonna pause the recording for now. We'll meet back at, okay, let's just say 2:30, and I'll stay over say 5 to 10 minutes. Sound good? This doesn't go until okay, so we have some requests. I will pause my recording for now. Okay, so just to welcome everyone back. So we have a request of going through question 3 on the discussion worksheet. Just one moment. So to reiterate for anyone who wasn't here before break ended, or this brief bathroom break ended. So discussions are really going to be split, sometimes really heavy in terms of like mini lectures, sometimes heavier in terms of worksheet. Like I said, C1 next week is probably going to be really mini lecture heavy and really Q&A heavy, with like kind of examples sprinkled throughout, maybe from discussion worksheet, maybe just like pulled out. And the reason for that is because it's just conceptually very, very heavy, and it's hard to go through questions if you don't understand like fully what's going on first, especially if you want to kind of tackle exam questions after that. But for the week after that, like if you want a discussion heavy, like worksheet heavy, floating point is going to be probably worksheet heavy because we've already established the foundations in this discussion. Okay, so I'm going to share my screen and hopefully you can see it. Let's see. Can y'all see my screen? Yes, okay. The yeses are not is floating point a hard topic. I would say it's probably on the scale spectrum of like hard to not hard. It's probably on the slightly easier side, not because of like, oh, it's super, super simple or whatever, just because like you've already had practice with number representation and it's just an extension of that. That being said, practice is good for that because there is calculation involved. Okay, so let's see. Okay, so going through the pre-check really quickly, scanning through. 1.1 we talked about in terms of different interpretations of the same bits, so that would be true. Number 2 is it's possible to get an overflow error in 2's complement when adding numbers of opposite signs, and this is false because just thinking about what overflow and underflow is, I'll give a really quick overview just right now in a few minutes. But overflow is when you go past what's possible to be represented. So for example, if you only have 4 bits available, so like 1, 2, 3, 4. 1, 2, 3, 4. Overflow would be like, for example, if you had 1, 2, 3, 4 like this represented, and then you wanted to add a 1, and then the final answer would be this. So because we only have 4 bits worth of hardware space, this is considered overflow because in real life, what we're trying to understand or what we're calculating is we know that this is 15 and then we're adding 1. So the supposed answer is supposed to be 16. But in real life, because we only have access to 4 hardware bits, the answer that the system gives us is, oh, this is actually going to be 0, which 16 is not equal to 0. Does that make sense? What overflow is? Yes, okay. Underflow is kind of the opposite. It's going too small into what's be able to be represented. We'll talk more about that during floating point. So to answer this question, is it possible to get an overflow error in 2's complement when adding numbers of opposite signs? And the answer here would be no, because overflow can only really occur if like addition falls outside like of what can be represented. If we have something that's within the bounds and then something else that's like negative and within the bounds, that's going to bring us closer to 0 than say to the outer bounds. Does that make sense? So no, because a positive and a negative number value already within bounds. We'll get closer to 0. Okay. So I'm going to skip over these 2 just now pre-check questions just in the interest of time. But this one in particular I wanted to cover because we didn't actually talk about overflow. So looking at question 2, it's unsigned integers. So we have, barring these 2 sections, which I will talk about at the very, very end. This particular question is just discussing how we're going to be calculating different things. So in A to B, it's just converting back and forth between the different forms that we talked about. So decimal to binary, binary to hex, hex to decimal, etc. I would highly recommend going through this and see how much of the material you've retained so far, just to see like which parts you might need to reinforce on, like, oh, if you don't remember what the hex values are, that might be a good place to start. So The answers for this are all online already. But if you have a question in terms of how certain things are calculated, because it doesn't always write out the full explanation, feel free to post on Piazza about it privately or publicly in the discussion thread. IUC prefixes I'll talk about at the very end because they're pretty cool, but we don't really need them as of right now. Question 3, signed integers. Okay, so we talked about this a lot during the mini lecture itself. So we talked about how they work well with natural numbers, but a lot of calculations use negative numbers instead. So we can see we write the value. So this is mostly talking about 2's complement. So we can write the value of an n-digit 2's complement number as, and then we insert this math equation that we didn't sign up for. So it's going between summing up between 1 to n minus 2 to the. So this is, personally, I don't really like this, I guess, I don't really like this way of writing it because it's not very intuitive and it's very mathy. So if you understand this and you really like math, props to you, but my brain cannot process this. So what we can think about is like writing the value of an n-digit 2's complement number is kind of taking the positive and then reversing and then adding 1 or vice versa, like we talked about in lecture. Negative numbers, okay. Negative numbers, as a rule of thumb, will have a 1 in their most significant bit. Just as a note for the future, MSB sometimes will say most significant byte as well. Byte. And the reason for this is because oftentimes we'll be looking at, say, a memory address or something like that. And it will be really important to locate like, oh, which direction things are going in. We'll talk more about this next week. But just so you don't get confused, both of them are MSB, but either it'll specify in the question or it'll be really obvious based off of what you're supposed to calculate, whether it means bit or byte. Is that any questions? Okay. So moving on, we have we're going to skip over the mathy parts. Meanwhile, positive numbers will have a 0 in their most significant bit. And then we calculate this again. So it's just 2 different ways of calculating it. An easy way to avoid kind of math formulas is just to look at the most significant bit, identify whether it's 0 or 1, like we said earlier, and then compute it based off of what we know. So for positive numbers, it's just unsigned calculation. For negative numbers, we know if it's binary already, we take away a 1, flip it, and then take the negative of whatever result that is. So a neat trick for flipping a neat trick for flipping the sign of a 2's complement number. So going from, say, n to negative n or negative n to n, you flip all the digits and add 1. So note, this works. Going from positive to negative and negative to positive. So this is pretty cool that way, and it works because we have a limited number of bits at our disposal. Addition is exactly the same as with an unsigned number, so you can add the 2 because in mathematical calculations, this is also why we prefer 2's complement, but mathematical calculations, because the number sign goes in one direction and nothing overlaps, we can just perform arithmetic operations as expected without having to deal with it separately. And then there's only 1 0 and it's located at 0, 0, 0, 0, dot, dot, dot. So this is also really, really nice. So we know that all zeros is going to be 0. Can I scroll up a little here? Is that good? I'm not sure how far, sorry. Okay. I'll zoom out a tiny bit so I can talk about the next part. So I'll also post these along with the slides that I have. I'll probably either link them on the slides or somewhere in my drive that I'll link. But just as a note, I guess, depending on the worksheet, some might have more writing, some might have less writing. For questions, okay, A through C, assume an 8-bit integer and answer each one for the case of an unsigned number, bias number with a bias of -127. So we can see that 8-bit numbers, so we know 2 to the 8 is equal to 256. We use the standard bias because it's negative 256 divided by 2 minus 1, which is equal to negative 127. So we can confirm that negative 127 here is the standard bias. Okay, standard bias and a 2's complement number. Indicate if it cannot be answered with a specific representation. Cool, okay. So I'm going to give you guys a couple minutes to work on this. So the first question is, what is the largest integer? What is the result of adding 1 to that integer? So this is basically talking about, okay, well, what happens when we kind of quote unquote overflow? So I'll give you all a couple minutes to work on that. Let's see. I'll give you until 45. So 3 minutes to work on that. If you don't finish it, that's totally all right. If you finish it, you can move on to part 2.
So for this one, what is the largest integer? Do they mean like say the size of it, or do they mean like the exact integer that it is?
The exact integer.
Okay.
Mhm. So to confirm, does the 8-bit integer have a range of 2 to the 7? Do you mean in terms of which notation are you?
Like, sorry for the mute, but like binary representation, because it's 2, the range for binary interpretations is 2 to the n minus 1, right?
Oh, okay. I think I'll address this in a minute. Because when you say binary, like we talked about, all of these different versions are binary representations. Do you mean unsigned?
Yeah.
Oh, okay. I'll talk about this in a second since it's 45. Really quickly, also before we hit the end of section, I'm gonna drop the feedback form in the chat right now. Feel free to fill it out afterwards if there are things you want more of, if you want less of, just etc. And it can be anonymous if you want it to be. It's not collecting emails or names. But if you also want to follow up afterwards, feel free to leave some form of contact so you can reach out. But yeah, okay, so going through this, so to address, I guess, Darren's question, what is the largest integer? So when you talk about like binary representation, it really means any of these, because binary representation just means using ones and zeros instead of, say, 0 through 9. So you really have to be specific, say, when you're asking on Piazza or like clarification questions like, oh, which of these binary representations do you mean? So for unsigned, Darren was saying was like, oh, isn't the largest, like, remember we talked about the largest or the range being 0 to 2 to the n and then minus 1. So I think the first clarification question is the position of the minus 1 is really important because 2 to the 7 would work. So like 2 to the 7 is if you had, say, 2 to the 8 divided by 2. And that would result in 2 to the n minus 1 up here. This is when you want to split a representation across, say, two different groups, so negative and positive. So that's when the divided by 2 would happen. In this case, because unsigned is only 0 and onwards, we only have one group and we only need to take one value away from the uppermost bound in order to represent the 0. So in this case, then what we can have is our largest value is going to be 2 to the 8 and then minus 1 overall. So we know 2 to the 8 is 256. And if you don't know this by heart, that's okay. This has been 6 semesters of memorizing all of this. You'll get the hang of it, definitely. So 256 minus 1, that gives us 255. So are there any questions about how we got here? Okay, I'm assuming it's letting us sink in. So if we know that we also have 8 bits worth, and we also know that we hit the uppermost value, which is a power of 2 minus 1, then what is our representation of this going to look like, just without thinking? So what kind of 7 ones? So is it 7 ones? So we have 2, 3, 1, 2, 3, 4. 8 ones. Yes, so we have 8 ones. So you want to be really careful about that, because if you notice, like if you have 2 to the 0, that's going to be just binary 1. And then there's nothing like 2 to the 1 is going to actually require 2 digits to represent. It's going to be 1, 0. And that's because we start out this lowermost digit with 2 to the 0th value. So when you get to 2 to the 8, it's going to require 9 digits. So it's binary 1 and then 2, 3, 4. 1, 2, 3, 4. So in this case, this is not actually going to be the value. This is 255 is going to be 8 ones. So 1, 2, 3, 4. 1, 2, 3, 4. Does that make sense? Okay, cool. So if we take a look at this and it says, okay, what is the result of adding 1 to that number? What do you think we'll see? So 0, we have a 0. Anyone backing up the 0? Yeah, exactly. Computer die. Yes, overflow, exactly. So like we talked about a couple minutes earlier, this is going to result in overflow because like the problem specified, we only have 8 bits worth of space to actually use. So even though we know in theory, if we say we're going to add 1 to this, we know it's going to be a 0 by, let's move this over a little, 1 and then 0, 0, 0, 0. We know it's going to be 256 in theory, but in reality, we're not actually going to be able to represent all that. So we box it off here and it's going to be all 0. So exactly. Are there any questions for that part? Okay, so moving on to the next part, we have our bias form. So, okay. So we have our standard bias of negative 128, which is calculated from 2 to the parentheses, negative 2 parentheses 2 to the n minus 1 and then minus 1 overall. So what would our uppermost bound be, given what we looked at in slides earlier? If we know our lowermost bound is negative 127, what's our uppermost bound? Any thoughts? Yeah, okay, so we had 127 and some 128s and then a couple of other 127s. So yeah, it can be a little confusing to think about like, oh, what is the kind of opposing one going to be? But if we just kind of, I guess, keep it in our heads that we're going to, in standard bias notation, we're going to sacrifice a negative value for the sake of 0, then we're naturally going to have one extra, quote unquote, extra positive value. So it's going to be 1 larger than the magnitude of whatever the lowest negative value is. So this is only going to work in standard bias though. So if you say have some whack form of that, you're going to have to say, okay, I have this number of totals. So I have 2 to the n total. I'm going to subtract my negative representation. I'm going to subtract my 1, 0. This is going to be the total slash maximum positive. And then vice versa for negative. Does that make sense? Yeah. How do I remember? Yeah, cheat sheet. Also, it kind of settles with time. You noticed earlier, like I had double check to make sure that like this wasn't the floating point representation, which is slightly different. So it does come with time. I would recommend write it on your cheat sheet for sure, but also understand like why this is the case. So that way, if you see it on your cheat sheet, it's not like a, huh, why is this the case kind of thing. Okay, so in that case, we're going to have bias is positive 128. And so if we add 1 to that, what are we going to wind up getting? Thoughts? So if we have 128 plus 1, what are we going to get? Negative 127. We have a spicy answer. Negative 127 overflow. Yep. So this is again the concept of overflow. So you'll notice a pattern in all of these. If you have a largest integer, you add 1 to that, you're going to overflow to the lowermost value. So in this case, it's going to be negative 127 because that's our lowest value. In the previous question here, our lowest value was the lower bound of 0. So that's why we overflowed to 0, because we kind of went off the deep end. In this case, we went off the deep end and went all the way to the other side, but the other side was a negative value instead of 0. Does that make sense why there's a difference there?
Yeah, so if we kind of like follow the formula that you gave for number 2, so the total of bias would be 128 plus 127, right? And then you subtract 127, and then you add, and then you subtract 1 from it. Can you like?
I'm not sure. I'm not too sure what you mean. So
this you have this formula over there that gives you like the max positive, right?
oh, you mean this? Sorry. Yes. Okay. Okay. So the subtract here isn't like the value itself, it's how many of them you have. So yeah, in this case, 2 to the n, I'll use a different color. Hopefully this is clear. So we have 2 to the n, which is in this case 256. We know we have 127 negative values, so that's 127. We have 1 0 right here. 256 minus 127 minus 1, which is going to give us 128. So that's going to be our maximum positive, and that's how many positive values we have.
So we have 127 negative and 128 positive.
Yeah, and then 1 0, which is neither.
Okay, thank you.
Okay, so 2's complement is going to be pretty much the same thing. 2's complement, you'll notice, has a slightly different bounds than the standard bias does, which is also why like it's good to keep this on your cheat sheet even when you do understand it, because it's really easy to mess it up. So in 2's complement, we know that the largest value is actually going to be, let me use a different color to make it obvious. It's going to be positive 127. The reason behind that is because we actually sacrifice a positive number in this case, and so we have 1 extra negative number. Ask me why this is the case, why they chose 2 different things to represent. It's just, I guess, computer science like when they developed it, they were just doing their thing. So we'll notice that the ranges of biased and 2's complement are like shifted off by 1. So if we kind of overflow this, this is going to be negative 128 in that sense. Why is it just convention? Yeah, they do weird things. A lot of the time you'll be like, it's just the way it is because that's how it was developed. And it's really frustrating to hear, especially when you see something like that. It's literally the reverse, right? Like it could have been just so easy to say, I'm gonna like keep it the same. But yeah. Okay. Are there any questions for part A?
So for number 3, for 2's complement, what's the answer?
And so the maximum or the largest integer is positive 127, and then the which is going to be basically, so the way that it would be represented here is like, let's plot here, would be 1, 2, 3, 4. So you'll notice this is what I think someone said earlier for the unsigned largest value. You'll notice that this 0 is actually here. And in this case, it makes sense to have a 0 there and to have 7 digits worth of 1s because we've split the things in half, right? So half of the like basically the half with the 1 at the beginning became negative numbers. And the main difference that we have here is that we want to have zeros in the middle. And so we're going to, because like earlier we said, okay, we established that 2's complement somewhere. Oh yeah, there's only 1 0 and it's located at this value. So we're going to say, okay, well, we have, these are our positive values. And then let's use a different color. 0, be 1, and then let's just use X's for this. Oh, wait, too many. And 1, 2, 3. Oh wait, I have 1 too many ones here. That makes sense. There we go. So 8 digits. These are all our negative values. And then we make an exception by saying, okay, we have 0, 0, 0, 0, 0, 0, 0, 0. This is going to be our neutral 0. And so we can see why here we take it from the positive side, because if we say, oh, we're going to take it from the negative side, then in theory, that would mean we would have 1 and then all zeros. And that's just kind of like funky in terms of how the convention works. So yeah, it is kind of like a convention, but also like logic. It's like, oh, well, all zeros is the easiest way to represent a 0 and the most standard one. So we're just going to borrow it from the positive side, as opposed to bias where everything is shifted. Does that make sense?
So again, following the formula again would be the same, right? So you do 255 minus 127 minus 1, and then you get 127.
256.
Okay.
But yeah, it's the same same way. So, well, bias and 2's complement always be flipped. So I'm guessing you mean about the ranges and what's the maximum and what's the overflow. Not always. In this case, it is kind of the opposite because we use a standard bias. But you say if we had like a bias of like -15, it's not most definitely not going to be the case because it'll be 0 through 255 shifted down by 15 instead. So our overflow value would be -15, and then our uppermost value would be 255 minus 15, whatever that is, because I can't do math at 240. So it won't always be. So will the bias of -127 mean that it always starts at -127? Yes. So whatever the bias comes out to be, it's going to be the lower bound because it's always going to be 0 plus whatever bias that is. So if the bias were +127, then the lower bound would be +127, and then the uppermost bound would be whatever highest value that you have in unsigned plus the bias. Does that make sense? Okay. So with a bias of 0 would make it 0 through 256. So actually with a bias of 0, it's just unsigned representation. So it'd be 0 through 255, remember, because we can't get to that last 256. Yeah, it's a really easy mistake to make, don't worry. So how many negatives do we have? For 2's complement, I'm guessing. So for 2's complement, we have 1 extra. So we have 128 in this case.
We have 1 extra because
we borrowed all zeros, which technically would be considered a positive number. Like this is technically positive, but because it's 0, we just count it as a neutral. Because if we looked at this, we say, okay, 1 and then everything following it is negative, 0, everything following it is going to be positive. Technically, this falls, the 0 falls into the positive camp, but because 0 is just 0, we usually don't think about it like positive 0. So for the bias, we have a -127 because we subtracted 256 from 128 to get the lower bound. Not exactly. So for the bias, I'm guessing you mean, wait, okay. Hold on. So I'm guessing you mean this part. So we subtracted 256 from 128 to get the lower bound. So basically, okay, I'm not 100% sure I get the question in terms of the kind of the reasoning. So if you want to clarify, feel free. But the way that you can think about it is we have a largest value and we know that that's going to be the most that we can ever do given our current hardware, so 8 bits. So if we add 1 to that, it's going to overflow and give us whatever our lowest value is going to be, which in this case is -127, because that's what our bias is. And we know that the lowest value is always going to be 0 plus whatever the bias is. Yeah. Okay, cool. Okay, let's see. I guess we have, okay, we are technically at time. So if you need to head out, feel free to do that. I'm going to probably stick around for another 5-6 minutes, something like that. Yeah, so see you guys next week if I don't see you sooner in office hours. So to answer, why is the biggest for biases not 127? The reason for that is just because of the way that the bias works. So we borrow one from the negative side in order to, so we have one extra positive in that case. Does that make sense? Can I explain how you got the 2's complement in terms of for this, I'm guessing, right? So I'm going to move this. I'm going to put this as a star and then move it to the bottom just to make it a little bit more clear. But we can think about it as like, okay, what values do we have access to? Because say we could do guess and check and say, okay, like maybe like all ones is going to be the smallest, right? But that is time intensive and it's also not the fastest way that you can get to it. So you can use your understanding of how 2's complement actually works to find the the maximum and the minimum. So in the case of 2's, I cannot speak anymore. In the case of 2's complement, we know that we have 2 groups of values. We have our positives and then we have our negatives. So by our understanding of 2's complement, we know that the positive values are going to be binary of 0, binary, and then 0, x, x, x. So these are just random zeros or ones. We don't really care. This is going to be our positive camp, right? And then same with our negative camp, but the first digit is going to be a 1. So we know that we have 2 camps of things. If we don't count 0 right now, we're just going to say, okay, we have equal values on both sides. So split evenly, if we have 8 bits, we can represent 2 to the 8 number of values, which is 256 values. So if we had split it evenly, our negative side is going to have a maximum of negative 128, and then our positive side is going to have positive 128. But we do know that we're missing something. We're missing our 0, right? Because we haven't actually established what that is going to be. So we're missing our 0 in here. And so the good people of 2's complement decided, okay, we want to make it simple and say we're just going to have an entire however number of bits that we need. All zeros is going to be our standard 0. So that works out well because, well, we can say, okay, if we have 0 binary 1, 2, 3, 4, 1, 2, 3, 4, this is going to be equal to 0. That's fine and dandy. But we also know that anything beginning with a 0 is technically considered positive. So if we think about 0 as a neutral value, it's going to take 1 from our positive side, which means that, like, if we recall back to unsigned, if we take quote unquote something from our uppermost bound, then it's just going to shift that down by 1. So instead of being 128, it's going to be 127 here. And our lower bounds wouldn't change because we didn't take anything from this. Does that make sense?
I thought it would be like something like minus 127 and then 129 because like you're adding one number to it. They're adding 10 to already 128 numbers. So it will be 129 and then we subtract 1 from, or we add 1.
Where are
from,
you
like,
getting the 129 from?
because like you have 128 positive numbers, right?
You have
And then
128
we
what
also have
numbers?
this positive numbers.
Positive numbers?
Yes.
Yeah.
And then we have this, and then we also have 0. So
Right.
we account for that too. So 128 plus 1, 129.
So I think there's a bit of a misunderstanding, like how we get, basically we're saying we only have 256 total. So we can't like quote unquote add anything. So instead we borrow a positive number representation that could have been used for something else to use as a 0. Hence why we have 128 minus 1 positive numbers.
So basically you're giving away 0 to like the negative side.
We're giving away a 0 just to 0. Like 0 we don't count as positive or negative in computation, right? Like it doesn't fall in the positive spectrum, but if it makes it easier to think about, you can consider 0 a positive number and say 0 from 2 to the n minus 1 minus 1. That's going to be our positive spectrum. We have 128 of those and it includes the 0. And then we have 128 solely negative numbers.
But then to make it work, then we have to like subtract 1 from 128, which takes 0 away from the positives
Yeah,
and gives it to the negatives, right?
it doesn't give it to the negative. 0 is just counted as its own separate category, which is why right here we have -1, 0.
Oh,
So yeah, we don't count it as
separate thing,
positive
I
or
see.
negatives. Hence,
I see, I
it's
see.
128, 1, 127 in terms of counts.
Makes sense.
Mhm.
Thank you.
Yeah, so the point of splitting binary 0 and then 0, 0, 0 is to take 0 that we're missing into account. Yes, exactly. That makes sense?
Hello, can you hear me?
Yeah.
Okay, so after we split, we take whatever is on like the left hand side, which is like a 0.
Mhm.
What's the point of like, am I like replacing it with like the 0 that I'm missing?
What do you mean replacing? What are we, sorry.
I'm sorry, I get everything up to like the splitting part. Like
you mean this
how we
part?
have like the 0 missing. Yeah. And then we're trying to take the 0 from like the positive group.
Yeah,
What you're
so
saying?
I think this line, is that what's confusing? Okay, yeah, that was just to demonstrate like the most significant bit is a 0, so technically you could consider it a positive number. And yeah, there's no official lab today, but lab 0 is due, so the setup. We have, I think, open office hours that I was supposed to get to, just to, if you have any trouble setting up, but it's due today, no official lab. So yeah, even to answer your question, so the reason that like it's split here is because like it's just showing the 0 could be technically considered a positive number because of this feature, which matches here. It pattern matches basically. But because like logically speaking, when we say 0, we don't really think about it as a positive or negative number, right? So that's why we're saying, oh, we set it aside and we take it from the positives. But if it helps to think of 0 as a positive number, then we have, oh, -128 through -1, and then 0 through 127. So it's 128 numbers, 128 numbers.
But this is not always going to be the case, right?
It's for 2's complement, it is because of the way that it's set up. Like 2's complement is just centered around 0 and as evenly split as possible between the two. I think what you're thinking about is bias. That's not always going to be the case because it depends on what the bias actually is. Sometimes like the bias range won't even have 0 in it. Say for example, like instead of positive, we have like positive 127 here. Then our range is going to range from, let me do it here. Our range for that is going to be 0 plus 127 through 255 plus 127, right? And that doesn't even include 0. So bias itself, it shifts up and down. So we can't really consider, oh, it's evenly split. But the only reason that here we can see that like it kind of matches 2's complement, but not really, is because we're using a standard bias. Does that make sense?
Okay.
To find the largest, yeah, of course. To find the largest bias number, you just get the largest unsigned number, subtract, add the bias. So okay, to get the largest bias number, you get the largest unsigned and then you add the bias. Yeah. So just you can totally forget about subtracting anything when it comes to bias. It's always adding a positive number, shifting the range up, or adding a negative number, which is shifting the range down.
So for the 2's complement, again, like we are basically taking away the 0 from the positives, but not from the negatives, right?
Yeah, because we only have 1 0, so we don't need 2 of them.
Oh, okay. So we are counting 0 as a negative number then.
No, we're counting 0 just as a neutral number, but I'm saying if it helps you think about it, we can count 0 as a positive number because pattern matching, it fits like the standard of what a positive number should look like in 2's complement.
So even if we do that, then the range is still going to be -128, 127?
Yeah, because it doesn't change what our range is, it just changes like how we look at it. Like for example, we can say, oh, negative numbers is -120, oops, not 2, -128 through -1. Like that's clearly negative, right? And then we can say, oh, if it helps us think, we can say positive. Positive is, well, 0 through 127. Like this is clear. This is 120. Oh my gosh, I keep forgetting the one. This is 128 values. but this is also 128 values, right?
Mhm,
So we can see total, we have still 256 representations. It's just that we kind of like, we give 0 an honorary position as a positive number. Does
I
that
see,
help?
I see. Yes, it does, but like that, yeah. So why isn't it like 128 though on the right, on the range of the right hand side?
Because again, like if you think about this as like, let's say I'm gonna use this as a double star. If you think about it like as a unsigned representation, because we split things in half, let's say like we, instead of thinking about 8 bits, we're gonna think about it as having only 7 bits. So what is our unsigned representation when we have 7 bits?
0 and then 7 ones, right?
0 and what?
And then 2 to the power of 7.
7
Minus 1.
minus 1. Yeah, exactly. So we have a range of 0 through 127. So the reason behind this is because otherwise we could have 1 through 128, but that's not very useful, remember? So we're going to shift everything down by 1. So we start from 0 and end at 127 instead. And overall, this has 128 values. And then this also has 128 values, right?
Right.
Yeah. So we can think about that the same way as the positive side. So that's why we end at 127 and not 128.
Oh, I see. So our 127, basically the range of our positive 127 is from 0 to 127, which is actually 128.
Exactly. Yeah.
Okay.
Okay. Yeah, I do have to go now. Hopefully this helped. The recording will be up at some point between today and tomorrow.